Welcome to Statics EGN 3311. In today's lecture, I'm going to cover the general principles of statics. Right off the bat, let me explain to you today's objectives. You should be able to learn about mechanics and statics after successful completion of today's lecture. You should be able to explain the mechanics and statics, the different types of units, the two main ones that we work with, and we would also talk about rounding the final answers appropriately and apply some of the problem-solving strategies that I'm going to discuss today. Okay, so some of the activities that you can do on your own is to pretty much go over some of the quizzes that we have and pretty much all the activities that are listed here you can perform on your own or while you are watching this lecture. So there's a quiz that right off the bat I would like to start with. The subject of mechanics deals with what happened to a body when blank is / R applied to it. So it's important to realize that the subject of mechanics deals with forces. Well, it deals with what happened to a body when the forces is / R applied to it. It could be one body with one force. It could be one body that we apply more than one forces to it. So that's really the subject of mechanics. Also, if you look at reading quiz number 2, blank still remains the basis of most of today's engineering sciences. As you know, there are different types of mechanics in Newtonian, relativistic, the Euclidean, and Greek mechanics. They're all important branches of mechanics. Some are important than the other, but still Newtonian mechanics based on Newton's laws still remain the basis of most of today's engineering science. So it's very important to keep that in mind. I wanted to show you these quizzes, go over them with you before we actually start talking about mechanics and what is it that we try to achieve when we talk about statics. What do we try to learn here? So that's important to realize. What is mechanics? You might have heard the term before from your other classes. You may have not. What is mechanics? It's really the study of what happened to a thing that could be a body. Again, the technical term that we use for this class is a body or an object. A body is used more than an object. So when we apply the forces to a body at rest, what happens to it? In statics, we deal with body at rest, but in dynamics, we deal with the body at motion. The forces can be large. The body can also be large. An example is the wheel of a train that is shown here. When it is stationary, there will be a reaction from the ground to the rail to the wheel. There's an action reaction that goes on here, and that's just an example. Also, when we lift an object, the body, by a crane, as you can see, point A down here, then what happens to what kind of forces would be developed at the chain, and what would be the reactions, and so on. So that's really the bulk of mechanics. So different branches of mechanics. Again, rigid bodies, things that do not change shape. They divide into two categories of statics and dynamics. Also deformable bodies. These bodies, they change their shape when we apply the force to them. So they're rigid bodies and deformable bodies. Also fluid, which deals with incompressible and compressible fluids, that falls under the category of fluid mechanics. So we primarily staying on the rigid bodies, and we are down here in static. So the assumption is the forces are applied at a rate in which no dynamic response would be produced as we apply the force to a rigid body. We also, in order to quantify things and solve problems, we would use units of measurements, dimensions, and their appropriate units. Four basic dimensions: length, mass, time, and force. And we would use the Newton's second law. It relates force to mass and acceleration. We use this equation to develop our units of systems, a system of units, and we would pretty much try to stay consistent as far as the units are concerned. So the unit systems are two main unit systems we are going to use. One is SI and one is USCS, US Customary System of Units. In both systems, we have different units. Force, mass, time, and acceleration are related by Newton's second law, and the three of these. Oh my God, this is something here. Hold on a second. Okay, resume recording. I'm sorry for this. I almost lost the lecture. Okay, let's take a look at these unit systems, the International System of Units, SI units, and US customary. Let's take a look at those units. In length is measured in meter in SI, and foot in USCI, and time. Both units, both unit systems or system of units, they are in seconds. Mass is kilogram versus slug, and Newton is used for force versus pound that we use for force in US customary unit system of unit system. So again, we are going to solve problems, and we take a look at these units. Again, units that are given in the problem should be used throughout the problem, need to be consistent with the units. Unless otherwise indicated, you should just stay with the system of units that's given in the problem. For example, if it asks you to convert a torque value of 47-inch pound into SI units, then the answer would be 5.3102 Newton a meter. In the International System of Units, or SI units, there is no plurals. For example, mass M is 5 kilogram, not the kgs. Make sure you understand that. Again, we separate the units with a dot. Example, meter per second is m dot s, or sometimes dash is also used, but dot is most commonly used. The most symbols are in lowercase. Exceptions are Newton, Pascal, M, and G. So make sure you guys get these correctly. Otherwise, this M would be mixed with the meter, and Newton could be mixed with like other things. So it's important to realize that exponential powers apply to units. For example, centimeter multiplied by centimeter would be centimeter squared. Compound prefixes should not be used, and there are some of these prefixes that are used in the SI system. So when we do numerical calculations, we must have dimensional homogeneity. It's important to realize that all units must be homogeneous. We cannot combine the two systems together. For one problem, we either work with SI or we worked with US customary unit. We cannot mix the two, grab inches from for one as a unit for one dimension, and grab meter and then mix them together. that just doesn't work because they have different units. Dimensions have to be the same on both sides of the equation. We use an appropriate number of significant. Figure 3 is given, at least 4 for intermediate calculations and 3 for the final answer. So we use 3 significant figures for the final answer. For intermediate calculations, we use 4. Those we don't. We want to reduce. We cannot really eliminate the round-off error, but we try to significantly reduce the round-off error to the best we can. We want to be consistent with rounding off. If it's greater than 5, we round it up to the next number. If it's smaller than 5, we round it up to the lower number. 0.03521 would be rounded into 0.0352, and you can read more on your text. So let's see if you can quiz ourselves, evaluate the situation in which mass in kilogram, force, Newton, and length are the base units, and recommend a solution. The system units will have to be formulated. Only the unit of time have to be changed from second to something else. No change are required. The above situation is not feasible. As you can see, this is in metric units, so this is a metric system. This is no change are required. As you can see, mass is in kilogram, Newton, that's force, and length is in meter. So none of those are required, or the above situation is not feasible. Think about this and let me know what the answer should be, and just just check, make sure that you get the correct answer. Give the most appropriate reason for using 3 significant figures in reporting results of a typical engineering calculations. Can pretty much figure this one out as to why. What's the most appropriate reason for using 3 significant figures in reporting results for a typical calculation? There are certain problem-solving strategies that we use in this course. We call them IPE. It's a 3-step approach. We interpret, we plan, we execute. Interpretation involves reading, carefully reading and determining what's given and what needs to be found. And if it's not clear, we need to ask. If necessary, we need to make reasonable assumptions and indicate why we make those assumptions. That's the interpretation part. Then, after we comprehend all the information and digest them, then we need to think about major steps or a roadmap that will take to solve a given problem. Think of alternative creative solutions and choose the best one. But remember, these must be according to some kind of engineering principles. This part is extremely important. Both parts are very important, but the planning part, even if you understand the information and you understand what needs to be done, still, if we don't understand the correct formulation, how to set it up and how to solve the problem, that would really, it's not going to get us anywhere. Then execute, carry out your steps, use appropriate diagrams and equations, estimate your answer, avoid simple calculation mistakes, and reflect on / revise your work if necessary. This is really the bulk of the 3-step approach. Okay, here's another quiz called Attention Quiz for a Statics Problem. Your calculation showed a final answer as 1, 2, 3, 4, 5.6 Newton. What will you write as your final answer? If you want to round this up, it's going to be what? 1, 2, 3, 4, 5.6. Find the best answer. 1, 2, 3, 4, 5.6 Newton. 1, 12 kilonewton. 1, 2, 3. So the best answer is 1, 2, 3, 4, 5.6, right? Think about it. Now, number 2, in 3-step IPE approach to problem solving, what does P stand for? Position, plan, problem, practical, possible. P stands for plan, as I just discussed. Okay. Anyways, that brings me to the end of the slides for this rather short lecture to warm you up and get you ready